All right, so today we're going to be learning about IR spectroscopy. And while we're going through this, I'm going to be doing some examples from your handout with the sample IR spectra. So just kind of starting out with the basics, what you get kind of going through the different regions of the IR is that you're going to get a graph sort of like this, and on the bottom it's going to be plotting what we're going to call the wave number, and that has units of inverse centimeters. And this is related to the frequency that the bonds are vibrating and moving at. And so the way it works is they put the bigger numbers on the left side. And so the bigger the number, the higher the frequency. So the faster, more frequently the bond is moving back and forth. And then on the right side, you'll actually get smaller numbers. So those are the lower frequency bond movements. Okay, and so the regions in the IR are also going to be measuring in terms of what's called the transmittance. So we've already talked about kind of how the IR works, but here we're just going to talk about what it looks like on the spectrum. And so an important dividing line along the wave number axis is around 1500. So that's an important number. It's kind of a dividing line between what we're going to be calling the diagnostic region, which is pretty much everything to the left of 1500, and then everything to the right of 1500, so the smaller numbers is what we call the fingerprint region. And so the diagnostic region is just like what it sounds like. It's how we're going to diagnose or figure out the structure. And this is the important part of the spectrum. So this is where your most important information is. Occasionally we'll look at the fingerprint region for certain instances that we'll kind of sort out later in the semester, but normally you're only looking at the diagnostic region, and that will tell you everything you need to know for the most part. Sometimes we do look at the fingerprint for certain stuff. The fingerprint region, however, is unique for each compound. So just like every person has a unique fingerprint, every compound has a unique kind of pattern in the fingerprint region. So this might not tell you necessarily what functional groups you have, but if you know what functional groups you have and you're comparing like two compounds, you can compare their fingerprint regions to kind of make an identification that way. This is also, as I said before, it's the least important part. So a lot of times you're not ever even going to look here. All right, and then we're going to go through the individual regions of what's kind of going on here. But as we go to the left in the diagnostic region, this is where shorter bonds show up. So the shorter, and we're talking about bond length, the shorter the bond, the higher the frequency it's going to vibrate, right? Because they're going to be moving really quickly back and forth. And then the longer the bond, the farther to the right it will show up in the spectrum. So you can sort of memorize stuff, and there are a little bit of memorization to do here, but it's generally sorting the bonds from short to long. And that's kind of the general rule of thumb for kind of looking at and identifying IR spectrums. Okay, so let's go through and kind of do an overview of the different regions, where they show up. And then I'll go through each region kind of in more detail to kind of talk about what you would expect to see there. Okay, so again, we're going to start kind of, our dividing line is 1500. And again, this is our wave number on the bottom. I'm not going to label it here. But over here on the very far left, you usually go up to roughly 4,000. So I'm going to kind of mark some important numbers on the spectrum here. So marking 4,000, 3,000, 2,000, 1,800, 1,500, which is our fingerprint dividing line. And then depending on how your instrument is set up, it's going to go down to something around 500-ish in the fingerprint region. But the important stuff is here, 4,000 to 1,500. And again, that's the wave number. Okay, so kind of the first region we hit on the very far left of the IR spectrum, those are going to be our shortest bonds that we see. So in an organic molecule, I'm going to call that region that's kind of roughly 3,000 to 4,000. That's the region of stuff that is bonded to hydrogen. Because remember, hydrogen is the smallest atom. And so anything that is bonded to is going to have a very, very short bond, especially in organic molecules. That's going to be pretty much the shortest bond you can ever have. And so our common bonds that show up here are going to be, of course, CHs, OHs, and NHs. So just stuff bonded to H. Those are the shortest bonds we can possibly have. That's what's going to show up with the highest frequency to the far left of the spectrum. So after that, we get stuff that's not bonded to H. So all of those bonds are longer, but we can start dividing things into triple, double, and single bonds. So the more pi bonds you have, the shorter your bond. So you're going to hit triple and then double and then single bonds. And so triple bonds tend to hang out around 2,000. And these aren't super common. You will see them from time to time, but in this class, we're not going to encounter a whole lot of these. So these would be your alkynes, nitriles, stuff like that. And those tend to show up roughly around 2,000, and that's kind of significant because nothing else really shows up around here in the IR. So if you see a peak there, that's really important. Our next region is going to be down here, so sort of the 1,800 to 1,500 region, and that's going to be double bonds. And so that's going to be another really important distinctive region because the peaks that show up here tend to be very easy to see, which we'll talk about next. And so one of the most important ones you'll see here is the CO double bond, the carbonyl bond. But you also get alkenes and aromatic carbon-carbon double bonds. And those are very common bonds in organic molecules, so you often see stuff there for those. After that, we hit the fingerprint region, and everything to the right of the fingerprint region is generally going to be single bonds, so sigma bonds, to stuff other than H. So that's where you're going to get single bonds, but non-H. So like, carbon-carbon bonds, carbon-oxygen bonds, carbon-nitrogen bonds, etc. So halogens, all of that kind of stuff is down here. And all of those bonds, again, single bonds are very long compared to all of these other types of bonds. So they're going to have the lowest frequency vibrations, the lowest frequency stretchings, and they're going to show up down in the fingerprint. And so this region here gets very, very messy. So oftentimes, depending on the compound, you'll see a lot of peaks in the fingerprint region, and nothing down here is very definitive, which is why it's kind of where you don't normally look to do an identification of your molecule. So again, we have our shortest bonds over here, and then it's sorting down to the longest bonds, which are on the right side of the spectrum. So next I'm going to go through and kind of talk about the individual regions and kind of how you want to start looking at the spectrum and kind of identifying different things that you might see. And I'll show you some examples that are on your sample spectrum handout. Okay, so the first thing that I usually look for in the IR spectrum are the double bonds. And as we just talked about, that shows up roughly in the 1,500 to 1,800 wave number region. Okay, and so this is one of the most diagnostic bonds you can see. So if you see something there, that's really important and you don't generally want to ignore it. And so the main one that you'll see here are the CO double bonds, the carbonyl bonds. And in addition to just seeing a peak there, the way it looks is going to be very important. So these ones are going to be some of the strongest bonds you'll ever see. Strong meaning it has a very long shape, which means it has a very low transmittance. It's absorbing very strongly. So these are going to be very, very strong peaks, which means they're going to be very long in the spectrum. And they're also going to be sharp. So this is kind of the intensity, and this is more the shape. So they'll be sharp, which means it's narrow in width as opposed to being like broad. So CO peaks are normally strong, they're sharp, and depending on what they're attached to, they'll show up kind of in that region. So again, we're going to refer to these as carbonyl bonds. And the general number is that they're going to hover around 1700. Again, depending on exactly what functional group it is or what else is attached to, it can, be higher or lower than this number, but they're generally going to be around 1700. That's kind of the distinctive place you want to look on your spectrum. And so things like resonance, type of functional group, that kind of stuff can affect it as well. Okay, so just to kind of show an example of that, so the first one on your sample spectrum handout, here's just a really simple carbonyl compound. So this is acetone, which is like a simple ketone. And what we're showing here, so if you look here, here's 1500, 1600, 1700 right here. And if you look, you see a very strong, narrow peak right here. So that's correlating, that's kind of a classic carbonyl peak that you would see in the IR. You can also see here's 1500 right here, so I'm going to draw this dotted line. And so this is the fingerprint region here to the right. So all this stuff to the right doesn't really tell me anything about the compound, so most of the time you can just ignore that. This IR is telling me I have a CO double bond, which is consistent with the structure here. And then the other stuff we'll talk about once we get to those other bonds. Okay, so the next type of double bond that you'll see pretty commonly is a CC double bond. And so these ones are also going to be sharp, but they're going to be weaker than a carbonyl. They're still going to be very sharp, and they're going to be not as strong. So oftentimes if you have both, one will be a little weaker than the other, but not always. And so for this one, there's two different kinds of CC double bonds that you'll kind of see, and you could actually differentiate them in the IR. But you'll see alkenes, which of course would be like an isolated double bond, versus another common functional group is the aromatic ring. And again, the aromatic ring, not to confuse it with a cyclic alkene, it has to have all three double bonds in here, right? So it's a very distinctive pattern. If you only have 2 or 1 double bonds in the ring, that's not an aromatic ring. And that's important because that'll show up differently in the IR. Okay, so then here, again, these are gonna be weaker and sharp. The alkenes are gonna show up roughly around 1600 to maybe 1650, again, depending on what else is going on in the molecule. And then the aromatics are going to show up generally, you'll get 2 peaks a lot of the time, sometimes more. Again, it depends on what's going on the aromatic ring, but a lot of the time you'll get 1 peak hovering right around 1600, and then a second peak that hovers around 1500. Okay, so that's going to be a little different because the alkenes are generally going to be shifted a little farther to the left, closer to the carbonyl, and then these ones are going to be shifted a little farther to the right. And again, that has to do with bond length. So as a reminder, these are all in resonance with each other around the ring. And that resonance kind of creates a situation where these double bonds aren't fully double bonds. They're partially single, partially double. So they're a little bit longer than a pure double bond. So they're going to be showing up at a slightly lower frequency. Okay, so you can kind of differentiate between the COs, the CCs, and then aromatic versus alkene in the IR, kind of where they are. So 1700 is almost always a carbonyl. Somewhere around 1650, closer to 1600, usually past 1600, is going to be an alkene. And then if you see kind of a multiple peaks hovering around these 2 locations, that's usually an aromatic. And there's other evidence that goes along with these as well that we'll see in other examples. So just to kind of show you that in your sample spectra. So again, we have acetone from before. And so just to compare that one to the second example down below, methyl vinyl ketone, this one has a carbonyl, which again, we'd expect to see the CO double bond around 1700. So 1700 is right here. And we see a big strong peak here that represents the carbonyl. But then we also see a second sharp peak here. That's kind of, it's not quite at 1700, it's a little bit below. And so that's gonna be the CC double bond. Right, it's a little bit longer than the CO bond. And it's showing up a little bit farther to the right. You'll notice we also see some little guys over here, right? So there's this little guy here. This one's kind of in the fingerprint region. That doesn't really tell us much. So we see this kind of like these really strong ones. That's telling us what we need to know. And it's kind of overshadowing the other stuff that's happening. So on your next page for your sample spectra, there's an example of an aromatic compound. So another ketone, just to kind of compare what we're seeing here. So I'm going to move this one up. So in contrast to the one above, we still see, our strong, sharp carbonyl peak here at 1700. But then our CC double bonds are now shifted to the right a little bit. So you can see instead of being right next to that carbonyl, kind of in the 1650 region, we have this set of peaks. There's kind of like two little nubby peaks here at 1600. And then there's another one floating around 1500. So all of these peaks kind of in this region are probably the CC aromatic peaks. And that's kind of what you'll see when you see the aromatics. So it's a little bit different. You'll often see more peaks and then they'll be shifted farther to the right. So kind of a 1600. It would be unusual for an alkene to be at 1600. That would be pretty low. It can happen, but it's not the normal case. Okay, so let's talk about the next type of bond that we'll see. So that's kind of it for the double bonds for now. And we're going to talk about when we see hydrogen bonds. So things bonded to hydrogen. Because that's another important region. So usually I analyze the double bond region first, and then I draw my attention over to kind of the hydrogen bonding area. And so again, this is going to be the region to the far left on the spectrum. The 4,000 to 3,000 region, roughly that region. And so of course, one of the most common bonds we're gonna see are CHs, because we're doing organic chemistry and organic molecules have lots of CH bonds. And so this one is important because there's subtleties to that region where you'll see these peaks that kind of tells you a little bit about the hybridization. So depending on what hybridization the carbon has, that'll cause the CH bond peaks to show up differently. And again, it's all related to bond length. So if you have an sp carbon bonded to an H, that's going to be the shortest one. So it's going to be the highest wave number. And then, of course, sp2 and then sp3. Right, so this will be the longest. And so it'll have the lowest number out of the CH bonds. Right? And then we're also going to talk about, there's a special bond, so the CH in an aldehyde also has its own kind of special movement that it does that gives kind of a distinct movement. So I'm talking about the CH bond that's directly attached to the carbonyl. So this is a special kind of CH, we're going to call that the CH aldehyde peak. So those are kind of 4 different CHs that you'll see. And they each kind of have their own distinct look in the spectrum. So just to kind of draw just that region, an important marker for the CH bonds is 3000. And I mean like exactly at 3000. So oftentimes if you have a hard copy of a spectrum, you might want to take a straight edge like a ruler and actually draw a line down 3000 and see where the CHs kind of fall. And depending on the molecule, the CH region might be kind of messy because you might have a whole bunch of different CHs and they're all wiggling and vibrating as they go through the IR. And it's going to cause, instead of just a nice sharp peak like we saw for the double bonds, you're going to see several kind of jagged peaks. And it's not so much about the number of peaks. The number of peaks doesn't really tell you anything. It's more where they are. And so if it's to the right, so I'm just going to talk about these first three. So these are normal just alkyl CHs, meaning, you know, alkyl or, you know, aromatic or vinyl or stuff like that, as opposed to the aldehyde one. We'll talk about that one last. So anyway, anything to kind of the right of this region, and we're not going too far right. We're staying, you know, this might be like 2800 right here. So anything kind of in that region, that's going to be where the CH that are attached to the sp3 show up, so alkyl CHs. And then everything to the left of that, so again, we're not talking too far, maybe like 3100-ish. If it's to the left of 3000, that's going to be your CHs attached to an sp2 carbon. So that's going to be vinyl or aromatic CHs. The SPs will show up even farther. So SP CHs, and again, that's not going to be very common because that would be like on the end of an alkyne. Those will be a little bit farther to the left there. Okay, so these are the two big ones. These are the ones you'll see all the time. So you'll see kind of a jagged peak kind of sticking down in that region. And then if you see stuff to the right, that means you have sp3 alkyl CHs. If you see stuff to the left, that would be consistent with having like an alkene or an aromatic compound with H's attached. So the last one that you'll see is the aldehyde, the CH. So this is doing a different motion. So this is not just the normal stretching, it's doing its own little vibration thing. And it'll often be showing you kind of two peaks. One which will be roughly around 2800 and one that will be roughly around 2700. And again, that's going to vary, but usually you'll see those two peaks, and that's kind of quite a bit farther to the right than your normal CH peaks. So it's kind of distinctive. You'll kind of see it over here. So over here is where you'll see your CH aldehyde. And I'll show you some examples so you can kind of see what this all looks like. But that's where that stuff shows up. Okay, so let's look at some examples to kind of show you what I'm talking about with these CHs. And so I'm going to go back to our original examples that we started with. So the first one that we started with for the carbonyls, the ketone acetone. And so on this one, all of the H's, right, both of these methyl groups here, those both have H's on them, and these are sp3 CHs, so those are alkyl CH groups. And so what we would expect to see in our spectrum is that we would expect all of our CH stretching to be to the right of 3000. And so 3000 is right here. Again, I'm going to draw a little line. You can see our CH peak is this stuff right here. And it's not like one strong sharp peak, it's kind of a jumble of stuff. It's jagged, it's not super nice and sharp like the other peaks are. And so that cluster of peaks, that represents our alkyl CH bonding or sp3 CH bonding. And we don't see any other types because that's the only type in this molecule. So looking down here at our second example, we have both types. So again, if I look at my 3000 and draw a rough line up from 3000, you can see we have stretching that correlates to the alkyl CHs that are here on that methyl group on the end. But then we also have some stretching over here. And again, it's not always clear. It's not always a nice long peak. Sometimes it's like a little cluster or just a little bit of a peak over there. So this kind of looks like what you might expect. But that's kind of correlating to the CHs from the sp2 carbons. So the vinyl CH peaks. So it's kind of what that looks like. And so that's similar to what we would expect in example number 3 for acetophenone, because it also has the methyl group with the CH3s, or the CH for the sp3 carbons. And then we also have these aromatic sp2 carbons, which are going to have H's on them as well. So again, if we look at that 3000 marker, and you can eyeball it or try to draw a line, we have some stretching on the right side, which is our sp3 or alkyl CH bonds. And then we also have some peaks and stretching to the left of 3000. So that's going to be our CHs for our aromatic sp2 CHs. So we see that there. And you can see it's messy. It's not nice and neat like the double bond region. Okay, and so then one other example, so we haven't done this one yet, but example number 4, benzaldehyde. Right, this one, it doesn't have any sp3 carbons, so it's gonna have all sp2. So we have the stuff we talked about before. We have our strong peak at 1700, that's a carbonyl. And then we have some peaks hanging out. Here's 1600, 1500. This stuff, it's like weaker but still sharp. That looks like our double bonds from our aromatic ring. Kind of right in there. Again, sometimes with aromatics and other stuff, you'll see like little blips like this. They call those overtones. That has to do with other bond movements that we don't need to worry about. You want to focus on kind of the more major noticeable stuff. And then over here, if we look in the CH region, again, I'm going to draw my bond or my line from 3000. You can see this to the left. So this is what we would expect. This is our CH for our aromatic sp2 carbon hydrogen bonds. But then we have this stuff. And so this is what I was talking about for the special CH aldehyde bond. And so this is going to become important when we're trying to differentiate between different carbonyl functional groups. This is a distinctive bond, and it has kind of its own pattern. So you can see the aromatic CH bonds are here, and they're kind of littler. And in this spectrum, we kind of have this big peak, which is roughly around 2800, and then this peak, which is at roughly 2700. And so that pair of peaks together constitutes the movements that are characteristic to the CH aldehyde bond. And technically, yes, this is a sp2 carbon, but because it's a carbonyl carbon, it has its own special movements that give us this distinctive CH peak pattern. So it's a pair of peaks, usually. And again, depending on the compound, sometimes it's not this big. Sometimes it's smaller than the rest of the CH bonding peaks. Sometimes it's bigger, like it is in this example. So each individual molecule is going to have a different kind of distinctive pattern. But you can also see this is a little bit farther to the right than what you would expect for a normal alkyl sp3 stretchings. Those kind of tend to hover right here and touch on the 3000 line. This one's a little bit farther to the right. So normally alkyl ones won't go that far to the right. And so that's kind of a distinctive aldehyde pattern. Okay, so our next important bond to H is the OH bond, and that's going to generally be left of the CH region, which we just talked about. And this one's going to look a little different because it's the first bond we've talked about that is susceptible to hydrogen bonding intermolecular forces. And so as a reminder, hydrogen bonding, what that can do is that can stretch and affect what's going on with the bond. And so because of that, that can kind of affect what it looks like. And so it is kind of variable, but generally it'll have the same shape. And it also shows up in kind of this distinctive region where nothing else is really showing up. So this is a very important region of the IR to look at when you're trying to figure out your functional groups. And so the two main functional groups that you'll see with OHs are, of course, alcohols and then carboxylic acid. So those are the two organic functional groups that we will be looking at that have OH bonds in them. Right, so of course an alcohol will have just the OH and it's attached to an alkyl group. And then the carboxylic acid is an OH attached to the carbonyl. And so again, there's a carbonyl bond as well. We already talked about that. So you'll see that in the IR as well, but you'll also see an OH bond. And so again, we just talked about the CHs, and those are going to show up here around 3000. But for the alcohols, those are generally going to show up to the left, so somewhere over here. And again, it's going to vary depending on hydrogen bonding, the compound, etc. But it has a very distinct shape. So it's going to look kind of like this, where instead of being nice and sharp, like the double bonds, it's going to be very broad. So if you look over to the left of your IR and you see a big broad blob, that tells you that you have an alcohol. Okay, you have the OH bond from your alcohol functional group. For the carboxylic acids, it's not as obvious because this group is generally going through a lot more hydrogen bonding. It kind of broadens it a little bit more. And so it doesn't stick out as obviously as an alcohol OH does. What it does is it kind of overlaps usually with the CH region. So see this 3000 mark? And again, it depends on how much hydrogen bonding is going on. It depends on the specific compound. But what's happening is you'll kind of see something like this, where it'll start to dip. And then you might see your CHs poking out around the 3000 mark. And then it'll kind of broaden and go back up. So you kind of have an overlap of stuff going on, right? Because here, this is your CH region. But then this big dip here that's kind of going across it, that whole region is your OH from your carboxylic acid. And so it'll look a little funky, and sometimes it's hard to see, and if you're not looking for it, sometimes people miss it and they won't even realize that they have a carboxylic acid. So that's one that you want to be on the lookout for. Okay, but if you have a carbonyl, you should be looking for this as well. So you should be on the lookout, and we'll talk about that when we're comparing different spectra at the end. Okay, so just to show you some real examples of this. So in our first example from your sample spectra handout, this is just a kind of a typical alcohol. And this is like a textbook classic alcohol. So you can see here, there's this big peak, this big broad blob over here to the left of 3000. That's your OH from your alcohol. So that's a very classic looking one. And again, this can vary in size. This one's very, very strong. They're not always strong like that. Sometimes they're shorter, sometimes they're broader. So they'll differ in appearance. It doesn't look the same every single time. So the more examples you look at, the more you'll kind of get a feel for what those alcohols look like. And then this one, of course, we only have sp3 carbons. So if you look at 3000, right? So we have our CH for our alkyl groups, our sp3. And then here's 1500, right? So that's our fingerprint region cut off. So everything else is to the right of the fingerprint region, and we don't really need to look in here. This isn't really telling us anything. This molecule really only has the OH bond from the alcohol, and then it has the CHs from the alkyl group. And that's exactly what we see, and we don't really see anything else. So it's kind of a boring one, but an easy one to spot. So our next example is just to kind of show you how this is different. Here's a carboxylic acid. And so here I showed it twice. And what these two different spectra are, just to kind of compare, is that they've been taken using two different IR methods. And so again, what you'll notice is that depending on how the IR is taken, that can affect things, especially with groups that are involved in hydrogen bonding. And so I wanted to show you this because I wanted to show you how sometimes it's confusing to find the carboxylic acid OH. But one thing you'll notice is that you see the COO bond, the carbonyl, peak roughly at 1700, the strong, sharp peak. And then over here, you see a bunch of stuff. So like in this one, down below, you can more obviously see the CH bonding. So you can see like CH is poking out, but then over here, they're not poking out as much. But what you notice is it has this kind of weird, broad, blobby shape instead of the normal shape that CHs normally have. And so this kind of broad stretch here is the OH of the carboxylic acid. And same for down here. So this is kind of your kind of broad OH stretch here. and it's just overlapping with the CH peaks that are kind of poking out of it. So it's hard to kind of distinctively say what's belonging to the OH and what's belonging to the CHs, but they overlap in that way. And so you can see in the other spectra that we've done, they don't really have that blobby shape. So if we go back to the previous examples, like if we go back to benzaldehyde, you can see the CHs don't have that kind of broad blob pushing them out that you see here. So again, it's subtle, but if you know you have a carbonyl, you want to be on the lookout for that, because that could happen. So that's for your carboxylic acid. And then of course we also have, because it has an aromatic ring, we have the CC aromatic stretching that you can kind of see here, right? We have stuff hovering around 1600, we have stuff hovering around 1500. That's your aromatic stuff. And I'm labeling it here aromatic to just kind of differentiate that it's aromatic as opposed to like an alkene. All right, so the very last bond that we need to kind of talk about for the IR are the NH bonds. So our last bond that is bonded to H. And so, of course, the two functional groups that are going to have that bond are the amines and the amides. And really what we're going to talk about is the NH bond specifically, but keep in mind amines only have the NH bonds as part of their functional group, whereas the amides, the only difference is that you have the amino group attached to a carbonyl. So like in this one, you'd have the same NH bonds, but you'd also have a carbonyl in your spectrum somewhere. So anyway, for these ones, what's nice about the IR is that depending on how many NH bonds, it will actually appear differently in the IR. So we have to talk about the substitution pattern of the nitrogen. And so here we have a primary amine, a secondary amine, and a tertiary amine. And of course the substitution pattern is just talking about how many carbons are attached to the nitrogen. So primary has one carbon group, one alkyl group, secondary has two carbon groups, and then tertiary has three carbon groups attached. And so in a primary amine, that's important because primary amines have two NH bonds. Secondary amines only have one. And the tertiary amines don't have any. And so that's going to correlate to how it appears in the IR. So for the number of NH bonds you have in your molecule, that's how many peaks you'll actually see in that region kind of corresponding to those bonds. So for a primary amine, we'll actually see 2 peaks. And for a secondary amine, we'll actually only see 1 peak there. So that can actually help you figure out the substitution of your amine as well, which is useful structural information. Of course, tertiary amines, you might have one of those. You won't actually see any NH peaks, but that doesn't mean you don't have an amine. It just means you don't have a primary or secondary amine. There's always a possibility that you have a tertiary amine. And so you have to look for other types of evidence to kind of sort that out. Okay, so just to kind of show you what that looks like, again, it's going to be in the same region on the IR as the alcohol OH. And so on your handout, we're going to look at, I'm going to skip this one for now. Let's go to number 8, the amines. And so if you look here, on this one, we have cyclohexylamine, which is a primary amine. Again, that means it has 2 NH bonds. And so if you look over here, this is the NH bond area. So it's over here, it's past 3,000. It's roughly, this one's just short of 3,500. And you can see it sort of looks like it's not as blobby and big and broad as an alcohol OH. It's more defined, and you see these 2 little peaks here. And so that's kind of a signature, that's an NH stretch for specifically a primary amine, because there's two of them representing kind of the different motions, the asymmetric and the symmetric motions you can get from the two NH bonds. And so for this one down here, piperidine, that one has only one NH bond, so that's a secondary amine. And so over here, it's in the same location, the peak, but again, there's only going to be one peak representing the motion of that one NH bond. So this is the NH bond over here, and because there's only one peak, that represents the secondary amine. Okay, and so again, if you look at these, if you compare these to your alcohol spectrum, even if there's only one peak, you can see this looks different than an OH peak. So again, bringing back the alcohol spectrum from before that we were looking at, right? OH peak, again, that's going to be very broad versus an NH peak, which isn't super sharp, but it's also not as big and round as an OH peak. So it does look a little bit different. Okay, so that's for the amines, and that's the last bond I wanted to cover. But before we end the lecture, I wanted to go through and kind of give some tips for talking about and differentiating carbonyl groups in the IR. So these are kind of solving tips for that. Okay, so to kind of go through this, again, there's kind of similar things in the IR that you'll see. And so some common functional groups are, of course, ketones, aldehydes, esters, and carboxylic acids. So those are some of the most common ones you'll see. And I'm going to abbreviate carboxylic acid. So these ones can often look very similar in the IR because they all have the carbonyl, the very distinctive carbonyl bond that we've talked about. And so for these ones, things that you might want to be on the lookout for are like what else is going on. So all of these have a carbonyl group. And that's going to be the peak that's around 1700. Again, that can vary. And so that's not going to really tell you which one it is. So you'll see tables of numbers where it'll be like, oh, a ketone has a carbonyl stretch from here to here, and an ester has a carbonyl stretch from here to here. But if you look at all those numbers, for the most part, they all kind of overlap in their ranges. And where exactly that stretch shows up is going to depend also on what these R groups are. And so where specifically it is in this region is not going to tell you definitively which functional group you have. So you can hint at it, but you need to look for the other evidence in the IR to kind of definitively say which type you have. And so for me, the easiest ones to kind of sort out immediately are the carboxylic acid and the aldehyde, because they have other special bonds in addition to the CO bond. So remember, if it's an aldehyde, in addition to having your carbonyl, you're also going to have that special CH peak coming from the aldehyde CH. So we talked about that earlier in the lecture. So again, we're talking about this bond here, the CH bond attached to the carbonyl. And so going back to our example, we had benzaldehyde as our aldehyde example. So that's spectra number 4 in our sample spectra. So we're talking about this guy. So again, that's a pair of peaks, we talked about this earlier, that show up around 2800 and around 2700. And again, this one is kind of nice and clean. They're sticking out from the rest of the CHs. That's not always the case. If you have sp3 CHs, sometimes it can kind of overlap and get closer to these two peaks. And sometimes they're not as big relative to the rest of the CH. So sometimes they're smaller, sometimes they're big like they are here, but it's where they are that really matters, especially this one at 2700, because you won't get normal CH stretching there. So if you kind of have this pair of peaks and you have the carbonyl bond, that's kind of a signature aldehyde IR stretching pattern. So again, you'll have two peaks around 2800 and 2700. And again, these are just rough numbers. It's going to be very close to that, but they can move depending on what's in the rest of the molecule. So the other one that's kind of easy to spot that we've already talked about is the carboxylic acid, because it also has the OH group, right? And so that's the OH from the carboxylic acid. That's going to be very, very broad. And it goes across the CH region. So again, kind of bringing back one of our previous examples. So in our sample spectra, that's number 6, we talked about this. And so again, we're talking about here, the OH that kind of goes broadly across. It kind of makes your CH look more broad and it dips quite a bit. So that's more than just a regular CH where it'd be a little more pointy and have a flatter baseline around the edges of the CH region. Okay, so you want to be on the lookout for that. That usually means that you have a carboxylic acid. All right, and then the last two groups, so if you don't have the aldehyde CH and you don't have the carboxylic acid OH, then you probably have a ketone or an ester. And so these ones are gonna be very difficult to distinguish with IR by itself, but if you know what to look for, you can kind of distinguish them. And so going back to our very first sample spectrum of acetone, so remember it's gonna have a carbonyl, but you can see it doesn't have those peaks at 28 and 2700 for the aldehyde. It doesn't have that kind of broad stretching that makes the CH kind of dip down farther, so it's not a carboxylic acid. So it's probably a ketone or an ester. And so what you look for, so I'm gonna use this other sample spectrum to kind of compare to an ester. So on page 4 of your handout, sample spectrum number 7, this is ethyl acetate. And it's very similar in the spectrum to acetone because it's a very simple ester. And what you can see here is we definitely have our carbonyl. And again, we don't have the aldehyde CH. We don't have a dip for the carboxylic acid OH. And so it's going to be very similar to the acetone spectrum. But what you will notice is that for these ones, often you have to kind of dive into the fingerprint region. And so for an ester, you're generally going to have to look for the CO single bond. Okay, and again, this is going to show up because it's a single bond. It's going to show up in the fingerprint region. And so for these ones, they generally show up kind of somewhere between 1000 and 1200. Often they're hovering around 1100. So for this one, it's most likely going to be this guy over here. And usually if you're kind of trying to figure out if you have an ester or not, you kind of want to look for that. And those are going to be sharp and generally pretty strong. But again, it's not 100% definitive, but if you're looking for hints to kind of distinguish between those two functional groups, that's what you want to look for ester versus ketone. And so just to go back to the acetone spectrum and compare, you can look that like around the 1100 region, there's no strong CO peak here. There is this peak here, but this one's past 1200, so that's a little bit far away for an ester CO peak, so that's likely not it. There's also this little peak here, but this is not very strong, so I wouldn't worry about that. What you're looking for is a very strong, sharp peak around the 1100 region, and that's usually the difference between esters and ketones. It's a subtle difference, but it is there if you're looking for it. Okay, so I'm gonna put that in the notes. So an ester, you might have a CO single bond in the fingerprint region, and that's going to be roughly around 1100, and it's going to be strong and sharp. Okay, and of course you'll notice the one I didn't talk about here were the amides, and so I didn't talk about that because it's kind of like the same thing that we just talked about with the NH groups is that you'll have the carbonyl, but then you'll also have NH usually. And of course it depends on if it's primary, secondary, or tertiary, because you're only gonna see NH if it's primary or secondary. Okay, so we just talked about that bond, but that's what you'll see for the amides. And of course the amides, we just talked about, have a carbonyl with a nitrogen on there. Okay, so that's it for kind of like the major IR information that you need to know for this class. As we need to know other details, we'll bring those up as we go through the course. A couple of other just random peaks that I wanted to talk about that you might see that can sometimes confuse students. I'm going to use these examples to just kind of show you, is that sometimes for ketones, you can actually see, you'll see peaks over here, kind of in that alcohol OH, NH region for the amines and the alcohols. So on these first two sample spectra, samples 1 and 2, you can actually see there's these kind of peaks over here. And that's not part of your compound, and that's actually a common peak kind of thing that you'll see in ketones, sometimes in aldehydes, which is usually due to contamination by water or other stuff like that. And it's not actually part of the compound or anything that you need to worry about. But a lot of times this confuses students because they'll see this and they'll think, oh, this is an NH or this is an OH, and it's not. And so that's kind of difficult to sort out as we go through the class. If you have examples like that where it's confusing, just ask about that and we can kind of go through it. But you'll notice these aren't that big round blob that you get for like an alcohol. And they're also they're not defined and sharp like they were for the amine NHs. So they're kind of just these blobs that you get in the IR. Another one that you'll sometimes get confused by is that sometimes when you have primary amines especially, you'll get this kind of blobby peak here. And so this is outside of the fingerprint region. It's roughly between 1600 and 1700. And this has to do with different motions from the NH bond other than the normal stretching motions. And this will show up, but you'll notice it's not sharp. So it's not due to a double bond. So this is not like a carbonyl or an alkene double bond. This is just part of the NH2 group. And you don't need to worry about this either. You don't need to label it, but you will see it, and don't let that throw you off either. That's another thing that can come up. The last set of peaks that you might see come from aromatic rings. And so going back to this one with the benzaldehyde. So whenever you have an aromatic ring, similar to what I just talked about with the NH2 group, is that you'll start to see sometimes a bunch of peaks here. And they call those aromatic overtones, and again, that has to do with other types of motions that the aromatic ring is going through. And again, you never need to label these, but if you see stuff there, don't let that throw you off. Again, if you see stuff in this region, so 2000 to 1500, those are going to be sharp, strong peaks. They're not going to be these little tiny peaks up here, so you don't need to worry about that. All right, so that concludes our talk on the IR. So I'm going to stop it there.